So I will. Today is Wednesday, December 18th, 2024, and today we're joined by Renee Hannon for our final Christmas edition of our class. So welcome, Renee.
Thank you, David. Well, I'll just start out with a brief overview of my background. I'm a geologist and I have a master's degree from the University of Texas at Dallas. And after I got my degree, I headed north to Alaska and been there ever since, except when I snowbird to Florida. And I basically have 40 years of work experience in Alaska as a sedimentologist. And what we did, we constructed paleogeography maps with a focus on looking at ancient shorelines during the Cretaceous and Jurassic periods. So that was 60 to 100, 200 million years ago. And the way we did this, we incorporated in a lot of surface and subsurface data to generate these maps. And in particular, we did a lot of work with cores, but these were rock or sediment cores. So I retired 5 years ago and became interested in the younger Quaternary period, which is about 3 million years. And of course, a lot of that data, at least the past million years, comes from ice cores. And that's what I've spent the last 5 years kind of on and off as a hobby researching. So I'll go ahead and share my,
So your work, what your geological work was oil and gas exploration, I guess.
yeah,
That's
yes,
what
it
you.
was. And that's where you pretty much find a lot of the reservoirs are in these paleo beaches. The beach shorelines are some of your best ones.
And do you believe there is any abiogenic oil?
No, not really.
Some people say there's oil too deep to be biogenic. You don't buy that.
There is, but well, no. It's mostly organic material, plants. That's where the oil comes from.
And it was mostly laid down 230 million years ago or something.
Oh, the source rocks for the
Well,
oil,
yeah.
they're all different ages.
Ah,
Yeah, they can be as young as Paleocene, Cretaceous, hundreds of millions of years ago.
hmm.
So,
Interesting career. All right.
all right. So I'm going to
Let's
go
jump
ahead
in.
and share my screen here.
Be sure to differentiate between Antarctica and Greenland because we don't know the names of all the cores.
Right.
Okay.
Okay.
Corin, can you mute your mic, please? Thank you. Okay, take it away.
All right, so what I'm going to focus on today is ice core CO2 concentrations. And David asked me to talk about the uncertainties associated with the ice cores. And I am going to go a little bit basic here. I'll start with some of the glacier types. We'll look at some of the CO2 sampling methods. Um, and then I'm going to talk about some of the alterations we see with CO2 as the uh, snowflakes turn into ice and it's buried deeper because there's a lot of um, questions about the CO2 that you see in ice core. And then basically we're going to look at some of the data, not just the interpretations of the data, but the actual data points themselves. And I was going to try to keep the questions towards the end, but if you have a burning question, you can ask me.
And you want to tell us also about temperature reconstructions too, or we're just going to focus on
I
CO2?
think we're just going to focus on CO2 right now because temperatures are a whole nother topic, and we can do that at another time if that's okay.
Great. Sure.
I have a few backup slides on that, but I think focusing on CO2, there's quite a bit of information involved in this.
Sure.
So glacier types, there are basically two glacier types. One is the ice sheets, or what they call continental glaciers. And uh, to be a continental glacier, you have to be very large on a scale of greater than 50,000 square kilometers. And there are only two ice sheets or continental glaciers on the planet. One is in Greenland and one is in Antarctic on the polar regions. And so, just a few fun facts on the glaciers. They're huge. Greenland is like the ice sheet on Greenland is 3 times the size of Texas, and it's up to 3 kilometers thick. So, if you do some of the math on it, it contains 2.9 million gigatons of ice. Now, you'll hear in the news quite a bit, we're losing 700 gigatons per year. But if you really take a look, that's a fraction of a percent of the ice sheet. To melt all of the Greenland ice sheet would take more than 10,000 years for it to melt and raise sea level. I think they're saying about 7 meters. So that's a long time. And Antarctic ice sheet is even bigger. It's 8 times the size of Greenland. It contains 24 million gigatons of ice. And if you look at it, it's actually losing less ice than Greenland, and that's because it's in a colder region. But it would take over 160,000 years to melt that ice. So by the time these ice sheets melt, we will be in the next glacier period.
You're saying at the current rates.
At the current rates. Now,
Right.
if those rates increase or
Right.
decrease, and they do, they vary every year. But yeah, just looking at the current rate, I think that's over the past 5 years, something like that.
Yeah.
So you'll get a few fun facts here and there. So you should be able to, when you see some of this data, ask some really good questions. So the second type of glaciers are what they call valley or alpine glaciers. You'll see these in the Swiss Alps. They're in Alaska. They exist in mountainous areas, and they tend to flow down valleys in between these mountains. And in the 1970s, when they started getting temperatures and from the glaciers, and then they figured out they could the gases were trapped in some of these glaciers. They started, looking at all kinds of glaciers to fill in between the polar region. And when they started looking at these valley or alpine glaciers, they can get paleo temperatures from them, but they're essentially at melting point. They're what they call temperate, and CO2 has a really high solubility in water. So basically, what happens is when they started looking at the data from these valley or alpine glaciers, they were seeing parts per million of over 1,000. So it was really, that's when they started researching it and figuring out some of the solubility of CO2, and that the data is unreliable on valley or alpine glaciers. So the first question when you see CO2 and you see somebody showing you 1,000 parts per million over the last million years, ask them, well, what glacier is that from? Where's that ice core from? And if it's from a valley or alpine, you can look at the temperature, but don't believe the CO2 readings. They're not real. So the second thing is that all the CO2 data that's accepted by the scientists are only from Antarctic ice cores. And when I first started looking at this 4 or 5 years ago, I'm like, why not Greenland? And I went in and plotted up all the Greenland data, and actually some of my first blog articles were on Greenland, looking at the CO2. And basically, Greenland is warmer than Antarctic. It's still pretty cold, But what happens is in the summertime, you get melt layers. And there's a picture of a melt layer here in the ice core. They're, like centimeters thick. And these summer melt layers are the same effect. When they melt, CO2 is very soluble, and so you can get really high readings in these melt layers, like 2,000 parts per million CO2. And I think I even remember last year or this past summer, people were talking about it raining on the Greenland ice sheet. So you can see some of these in the core, so you don't want to sample them, but there's still, a shadow zone where the CO2 readings aren't very good. The other thing they found out about Greenland ice cores is that it contains a lot more impurities than the Antarctic ice cores. It has a lot of ash from the Iceland volcanoes. You get a lot of dust there. And these particles tend to, the ash is acidic and you can get acid carbonate reactions. So a lot of times when they started plotting all the Greenland data, they had highly variable CO2 measurements. And so these were some of the issues with the Greenland ice core. And then the last thing is the seasonal influence. I don't know if you've looked at some of the modern temperature readings, but in the northern hemisphere, you have a lot more vegetation. So you can get summer, winter fluctuations of CO2 by 20, 50 parts per million, whereas you don't see that in the Antarctic. And that's pretty much why they use the Antarctic data. And the last thing is the Antarctic has a lot longer ice core records. It goes back 800,000 years, whereas Greenland only goes back 100 to 120,000 years. So most of the data on CO2 is all from Antarctic ice cores, and that's what I'm going to be talking about.
I have one question. Can you tell us a bit about the technology and equipment that samples this and that
Yeah, that's my next
we're
slide.
going to talk about? Okay.
So basically, this is the butt end of an ice core. And they're anywhere from 4 to 6 inches in diameter. And here you can see where they sample the ice core for different elements and species. Here you can see where they do the isotopes and they do oxygen isotopes, and that's where they determine the water chemistry and the temperatures of the core. So you can see the little, and that's of the ice matrix. Then they do physical properties, they do chemistry, they look at the sodium, potassium, silica, and then this large sample here is where they do the samples for the gases. And you can see it is the largest piece because the gases are dispersed in tiny bubbles in this ice core. So when they first started doing in the 1970s, when they got this ice to get the gases out, they did what they called a wet extraction. And that's basically where they went in, took the sample and heated it under ice under vacuum. And they were experimenting and we're getting a lot of variable CO2 measurements. And again, remember what happens when you get water with CO2, it's highly soluble. And then the second thing they found out was that there was contamination with some of the water chemistry or the impurities in the core, like we talked about, acid carbonate reactions. So then they went in the late 70s, early 80s to a dry extraction. And this is where they take the sample and they mechanically crush up the ice. And it's kind of, these names are exactly what they do. This one, they get a bunch of needles and crush up the ice core. Here they hit it with a ball mill or an ice mill and crush it up. And one of the drawbacks, this is better than a wet extraction. So a lot of the cores have used this kind of mechanical extraction. But one of the things they were looking at was because the CO2 is trapped in these little tiny bubbles. A lot of scientists felt they weren't getting all of the gas out. Some of it was left behind because they couldn't crush the ice as fine as they wanted to. So the technique they use today is they sublime the ice. And that is supposedly 100% extraction efficiency. And the only problem with that, the con associated with that, is it takes a large piece of the ice core and it takes a long time to sublime the core. So they don't want to, a lot of scientists don't want to wait that long. And then post-extraction, after they get all this, collect the gas, they use standards to calibrate the equipment, and then the gas is measured either via infrared or mass spectrometer. And the infrared is the exact same way they measure the gases that they capture at Mauna Loa, present day. So the next thing I want to talk about is data uncertainty. And most of the remaining slides now are going to be dry extraction and Antarctic ice core. So whenever you see a CO2 measurement and it's really out of whack, or you want to know more about it, those are some basic questions you can ask. What was your extraction method? Where was the ice core sampled from? So the instrumental is the data uncertainty is very low. It only impacts the CO2 by 1 to 2 parts per million. The other thing I do want to talk about is that there's Jaworski he did a publication after a lot of the CO2 data was coming out on ice cores, and he was the one that was very negative on the ice core data and had a lot of questions about it. So I'm going to address some of his questions, not all of them, of course, but a lot of time. So this was an Antarctic ice core from SIPL. And you can see that there's a couple readings that are much higher, and they have a dashed error bar associated with them. And this dashed error bar was where the scientists noted drilling fluids in the cracks of the ice. And so when you see drilling fluid in there, that means that the ice core fractured somehow. And so your CO2 measurements are unreliable in that particular measurement. And so scientists frequently note outliers or exclusions, and they frequently don't even plot this data, they just note it. So there are some issues with those two data points. It is a common
Good
practice.
question. Are you going to show us a map at some point so we know where these cores are?
Yes.
Okay.
Yes. So I'm just trying to talk about through the basics, and now it's going to we're going to talk about the firn to ice transition and how it impacts CO2. So basically, when you transition, you start out with a snowflake, and these snowflakes accumulate, and then they begin to degrade. So you lose the sharp edges here into this granular snow, and they continue to degrade until they're like these little balls. And these little balls are called firn. And it's a fairly slow process. Continued snow accumulation, and these little balls compact together until eventually they turn into glacier ice. And it is dependent on snow accumulation rates and temperatures. So in high snow accumulations where you're getting a lot of snow, you can go through this process in about 50 to 100 years. But in low snow accumulation sites, it can take 100 years for you to go through this process. And so the impact on CO2 concentrations is the age of the gas and the gas diffusion or averaging during this process. You can see in this firn here, you still have a lot of black holes. It's still in communication with a lot of the atmospheric gas. And you also get, through this process, gravitational fractionation where CO2 is a heavier molecule, so it will tend to fractionate out, but it is fairly minor. It only impacts CO2 by 1 to 2 parts per million. So I'm not going to really discuss that, but all your CO2 measurements are corrected for gravitational fractionation. So this is, I'm going to spend a little time on this. So we're looking at a geologist's favorite way to look at things, and that's from this in depth. So here we have the surface, and here we're going down to 120 meters in depth. And this will be the only slide where I show you depth. All the other temperature profiles are usually in age, so they are flipped. But here you can see the snowflakes, and they're being compacted like we discussed. So you get this fern, and I have CO2 at the surface over here. And then I have density, which is very easily measured in snow, and it's very common. At the surface, it's about 0.55, and then by the time you're around 50 meters, you're densifying. The snow is going through densification. And over here is where you have pores. So the pores are the little holes in between the fern. And as those fern balls get compacted, those holes start to close up. So this is the amount of open pores. There's about 40% of the space is open. And by the time you get down to here, you're looking at about 5 or 10% open pores, and all the rest are closed. These are closed pores. So this is where your gas is starting to trap, and it eventually forms these little bubbles, and that is where the gas is trapped inside these bubbles. And the last thing I want to talk about is dating ice age versus gas age. So when they do the oxygen isotopes to get temperatures, they date the matrix, the snowflakes, the snow crystals. And here you can see over 120 meters, this age is about 80 years old, and around 60 years is when you're starting to trap the gases, the atmospheric gases. However, because you get diffusion, like the gas is in communication with the atmosphere up here, and then by your time you're down here, the gases are diffusing with each other until they're trapped. And once they're trapped, you're now at a gas age of 0. So there's a difference between the gas age and the age of the ice when they measure these gases. And this was one of Jaworski's key points that he talked about. So we'll keep going through this a little bit. I'm probably really getting into too much details right now, but how they determine how the age is distributed when it's trapped is by modeling. And this is actually the biggest effect that you have on CO2, is it is averaged over several years while it is being trapped. So here you have age 0 to 25 years, and then you have the age distribution. So at the atmosphere to 1 meter, it's all atmospheric equivalent that year. But by the time you're down at 80 meters, on this blue line, the age of the gas that's being trapped in the bubbles ranges from 8 to 15 years during the mode of this point, and that's how they model it. So at high accumulation rates, where you get a lot of snow, 100 centimeters per year, you can get an averaging of the snow. The gas is averaged over 10 to maybe 50 years. So that would be like taking the atmospheric gases that we have today that we measure and doing an average over 10 years or whatever. It's pretty equivalent. But you can imagine where you're not getting a lot of snow and it's taking a really long time to trap and bury these gases, you can have an average of over 100 years. And this just illustrates the different age of the gases trapped to the age of the ice. So we already talked about trapped gases younger than the age of the ice. And then once it's in the bubble, it ages with the ice. And this is referred to as the ice age, gas age delta. So whenever this is a plot you never see in the literature. What I plotted here are the gases that were measured in their ice age. And you can see, they don't really line up at all, but you can see little events, like this little event here looks like this little event here. And basically, because they're all at different snow accumulations, and you need to move them to their gas age, which is what this next slide looks like, you can actually see now that they line up quite nicely. And I even have atmospheric CO2 plotted on here from Cape Grin in the southern hemisphere in the blue line. And you can see now that we have very nice overlay of these gases. So that's the other thing, whenever you see CO2, it's in a gas age. So, all right, this is what Dave was waiting for. Now that we've kind of looked at the process, these are some of the key ice cores. And this is Antarctic. So the center of East Antarctic here is where you have very low snow accumulation rates, and it's up to 5 kilometers thick. So these are the cores where we get very long-term data from. And you can see, I'm not going to go over this whole chart, but it's just a comparison. It's a nice reference. I use it all the time. So it's a list of the ice cores, the accumulation rates, which are, over 100 centimeters of ice per year, down to about 3 centimeters for these cores, Voskok, Dome C. So that's very slow. And you can see the temperature ranges. Here, this is the gas age shift, which you really won't see that much, but a lot of times you might want to be interested in how that gas is smoothed or averaged over the years. And this is the gas width. So you can see it's about 10 years, which is very high resolution. These are high resolution cores. These would be much lower resolution cores. You got to talk about sample spacing frequency because it's not equal across the 800,000 years. So what I'm plotting here is age 0 to 800,000 years. And then this is the years between the individual samples. This is all the raw data. So every dot is a data measurement point. And it is inverted. So 1 year, 1,000 years. You can see a lot of it are, there's 1,000 years between individual data points. In the Holocene, from the last 1,000 years, you can see you have sample spacing that's, almost, it's less than 10 years, which is very good. And then you can, during most of the Holocene, you're looking at a 35-year sample spacing. Somebody went in and did a detailed analysis here where they improved the sample spacing. They went in and sampled at every 0.5 meters. So during the glacial periods, they got it down to 50 to 100-year sample spacing. And just another point on this, sample spacing is different than what we just talked about, the temporal resolution, which is modified by the Föhn diffusion, gas diffusion in the Föhn and bubble trapping. So you can have widely spaced samples, but a different temporal resolution. Now, I have seen people just say, oh, well, there's so many data points and divide it by 800,000 years and say the average sample spacing is 1,200 years between samples. Well, you can see that's not right. It's highly variable. So if anybody tells you that, you can go, no, you get a lot closer sample spacing here. So let's look at some of the data. Like I said, Antarctic ice core CO2 concentrations are considered the gold standard, and basically, Brighter is the CO2 curve through time that I always use. And basically, it's a composite of multiple cores. So again, we're looking at 0 to 800,000 years. And the one thing that's nice is that it is a continuous record. Some of the other CO2 proxy data types from plant stomata and phytoplankton are very, very discontinuous. So we have very nice continuous records. These are the interglacial periods that are shown in red. So this is where you have higher temperatures. During those periods, you also have higher CO2 readings of as high as 300 parts per million. During the glacial periods, where you had a lot colder temperatures by about 8 degrees C, you can see CO2 concentrations drop off quite dramatically down to 175 parts per million. Now remember, present day, today, we're looking at 420 parts per million, so you are like scaled off this chart. And that was one of the things that I wanted to find out. Was there any time in the past where we were getting CO2 readings this high? The other thing that you notice on the bottom here is that here are some of the 10 cores we've been talking about that, and they're color coded again in resolution. So these are your higher resolution cores where you have CO2 that's been averaged less than 50 years. This is about 50 to 100 years, and CO2 here is smooth or averaged over about 100 years. And unfortunately, our lower resolution cores in red are the ones that penetrate the longest. They're the deepest. Where you have the higher resolution cores, the higher snow accumulation rates, they don't go very deep until you hit bedrock or whatever. And there is only one ice core that covers the entire 800,000 years, and that's Dome C. So let's zoom in at different ages here. So we're going to zoom in over the past 1,500 years. And so now I think this graph is in age AD. That's the other thing you need to be a little bit careful about. So most of the core data, especially when it's over 800,000 years, is plotted from 0 to whatever, but 0 starting point is 1950. So that's the starting point of that. And so when I zoom in on this, it's like I go over to the AD scale where year 2000 is, we're all familiar with that. If I plotted it from the 1950, year 2000 would be shown like negative 50 years, and nobody really knows what that means. So be careful on these scales on years, and make sure you know whether you're looking at before present, which is usually 1950, or AD. So anyway, I plotted up, as you can see, there's 8, 10 cores here. And the one thing that I thought was, first of all, it overlies the modern station instrumental data quite nicely. Here's the firm data that we talked about. And remember, some of this is still in communication with the atmosphere, so you would expect it to overlie quite nicely. Here we're getting into the bubble zone, and these are generalized because for each specific core, they vary a little bit. But here we're trapping our CO2, and from this point down, from about 310 parts per million, all the data is frozen in ice, in these ice bubbles. And so we're looking at the high resolution cores. They're the ice averaging or smoothing due to the firn dissolution is only 10 to 30 years, and the sample spacing is less than a year to 20 years. So this is the highest resolution you can look at. And you can see that CO2 is fluctuating from, 270 to 288, 280. Surprisingly, they overlie quite nicely. I mean, you're really only looking at a 5 part per million variance in the range here. And so over the last 1,500 years, CO2 never really got higher than, 290 parts per million at the max. I mean, it was more like 285. So that is, over 100 parts per million less than what we're seeing at present day. So let's zoom out a little bit and see if the data is telling us anything different. So we're still, again, we're looking at about 10 ice cores, and every dot is the data point. It's not a interpreted curve. It's a data point. And you can see they still overlie quite good. There's good repeatability. And again, these are all the cores that have both high temporal and spatial resolution. We do see a little bit of scatter right here where we're going. This is the deglaciation going into the interglacial period. We see a little dip here around 8,000 years, and then it's gradually increasing. We see some highs here, and then after the little ice age, we ramp up to over 420 parts per million. So again, I just don't see any data in here that would suggest that we had those high of CO2 readings over the Holocene or the past 16,000 years. Oh, I just want to point out, this is some of the lower resolution data. Remember the Vostok? It's in the middle of East Antarctic, and it has very low snow accumulation. And it does tend to show lower CO2 readings, 5, 10 parts per million. So that is one thing the scientists, I think, could improve on, like they do with temperature data, where they do a mean or an average, or Monte Carlo, all the different temperature proxy data. I think they could take all the CO2 data from Antarctic ice cores and Monte Carlo that, and get more of a mean or average instead of just presenting, the Vostok ice core or the Dome C ice core, because both of those are very low resolution, particularly during the Holocene here. So, these cores probably are underestimating what the global CO2 was, not by much, maybe 5, 10 parts per million. So like I keep, searching. I mean, what I really want to find is what the highest value of CO2 was over the last 800,000 years. And I just can't find anything much higher than 300 parts per million. So I said, well, let's look at the wet extraction in Antarctic. Remember, that was the melt that had, if you're going to see any really high CO2 readings, let's plot that up. And so here is the blue dots are the wet extraction methods. And then the red is what the typical dry extraction from the CO2 composite is. And surprisingly, even with the wet extraction, you rarely break 300 parts per million. You do a little bit over here in the Holocene, and here you see a little bit of difference. So there could be some incomplete extraction during the dry methods here. But in general, and the wet does tend to be a little bit higher overall. But again, nothing greater than 300 parts per million. So I'm pretty comfortable with acknowledging that in the past, CO2, we really did not have large CO2 increases like we're seeing during present day. So this is my summary slide, just some basic observations that we've been talking about. CO2 from the Antarctic ice cores appear to be reliable, they're repeatable. The averaging of the CO2 concentrations during firn to ice transition is the biggest modification to CO2 and ice cores. And in some of the low accumulation sites like Dome C and Vostok, it can be up to 100 years. But over the Holocene and the most recent data, like at WAIS and Log Dome, you're really looking at fairly high resolution that should be comparable to instrumental data, present day data. And we saw the range of the CO2 from 300 parts per million to 175, and that even though a lot of scientists quote that CO2 has an uncertainty of 1 or 2 parts per million, that's really the instrumental data uncertainty at that data point. And I think when you look at all the data sets, you have a range of plus or minus 15 parts per million at most. I did include some basic references here that I can, leave this presentation with you, Dave, or whatever. But if you want to look at the data yourself, here's the best record for the data, Brighter, and all the individual ice core data sets. He has all the individual ones in there as well as a composite. And a lot of the data you can retrieve from the NOAA website. Some of these older papers, like this one from Gao in 1975, are really interesting because that's when they first started really doing some of the basic analysis of gas inclusions and looking at how the CO2 is trapped by bubbles, and there are a lot of clathrates or hydrates in the ice also. If you're interested in looking at the wet data, Kawamura has done quite a bit of work on that on the Dome Fuji. If you want more information on how the gravitational effects and some of the sampling methods and everything in the supplement, this more recent report by Nerbas Ellis in 2020, the supplement on that's very good. And then some of the Greenland data, if you're curious about the acid carbonate reactions and everything, Shimumi is, it's a very good reference also. So that's what I have prepared, David.
Cool. I have a whole bunch of questions.
Oh, no.
No, that's good. That I want to go, a little deeper just to dig in a little. So I'm going to ask you to go back to the beginning of your slides and walk through them because I kind of have like 1 or 2 questions for each slide, and maybe we can ask at that time. Okay.
Okay. Let me go back
Go back to the cross section first. That's slide number 4.
This one?
Slide number, yeah, no, slide number 4. Yeah. So I saw a documentary on this, and the first thing is it looks like the the engineering changed a lot over time. They designed different machines to extract. And you talked about wet and dry. I just want to ask, my understanding is that today the way they do this is they sort of feed it down continuously onto a machine that's melting and measuring, and it's continuous. They're not slicing it and they're not ratcheting, they're just sort of feeding it down, and it's automatically taking all these isotopes, chemistry, and gases all through one machine at one time. Is that right?
Um, yeah, I haven't seen that documentary. I've just been reading the literature. So I'm sure they're advancing the technology all the time.
Mm, okay, no problem. Let's go forward. I want to ask more about some of these cores. Keep going. So yeah, so here I wanted to understand the chart on the left has me a little puzzled because it looks like over time the CO2 concentration increases over a period of 100 meters, however many years that is. And I don't understand, why is the CO2 concentration increasing as you go down in meters? Or or is that just the natural, because
Yeah, this right here
yeah,
is all, this is still in communication with atmospheric gases, right? So you have open pores, so it's all diffusing, right? So this sample, I believe, was taken at 1900 or whatever, whenever we were at about 350 parts per million. And so with time, these Fern measurements, they're not only decreasing because CO2 is decreasing, but there also is some smoothing going on in here. And so,
so one
and
way to
the,
read this is that if I look at this, if I go from the yellow from the bottom to the top, what I'm seeing is the CO2 on the surface is increasing at that time.
right, right, it is capturing the CO2 increasing from this period of time to this period of time. Just
So
like
that 120 meters ago, the CO2 was less. Was
right. That's
300.
correct.
Okay, I see.
Right. So it is, yeah, at this time period, it is, you're going into the little ice age or whatever. So it is continuing to decrease through through time, over time. Correct.
So really, sort of on a meter by meter basis, it's a pretty accurate capture
It
of
is. It is.
even higher up in the gas diffusion layer.
Yep, it is.
It's not a mess,
No, it's
which
not. I
which is
actually, if you don't mind, I have a cross section that this lock-in zone or bubble zone is mappable across
mm,
all of East Antarctic. I
mm,
can show you what it looks like. It's actually pretty cool.
sure.
Um, let me see if I have it. Ah, so here I plotted some of the various ice cores. And so over here's East Antarctic, so and then West Antarctic where you have um, higher snow accumulation rates and everything. But and there the Fern measurements are very difficult to find. So I only have one, two, three, four, five. And so here on the South Pole, so they went in and sampled this fern at different years. And God, I forget the years on this, but like this was 2000, this one was 2001, and you or vice versa. And you can see the CO2 is actually decreasing. I mean, it matches the atmospheric CO2, and it's certain, yeah, it's a very uniform decrease. And then when you get into this bubble zone, it it decreases quite a bit, and that's because it's much slower. It's trapped in the bubbles, and now it's just moving with the age of the ice. So, and again, we're looking at depth. Sorry, I flipped it on you. As a geologist, I like to do these cross sections in
Yeah.
depth.
So the story this tells here, going as the bubble zone goes down to the right, is simply wetter to drier locations because,
Right, exactly,
right?
exactly. Right, higher snow accumulation.
Yeah,
Right, right,
yeah,
exactly.
right.
And
And
on
more,
the peripheral areas, like even these are on the peripheral area of East Antarctic, and because they're closer to the water, they get more rainfall, more snow accumulation.
yeah. So these depths are absolutely uncomparable because at the height of this plateau, which by the way, as she said, is 5 kilometers above sea level,
Right, it's high.
you can drill down 100 meters and get a huge amount of many years, millennia, much more time has gone by over 100 meters than down by the coast where it
Right.
piles up because you can get 5 meters in a year of snowfall.
Oh yeah, yeah.
Whereas at the top of the plateau, 1 meter in a year, this is the driest place on Earth.
It is.
That much precipitation is huge, and that's only 1 meter. So these are not comparable at all. The scale here could be 5 or 10 times difference in the number of years per meter,
Exactly.
right? And so this only goes down and to the right just because you've placed them from wettest to driest. That's
I
all.
did.
Yeah.
Yeah.
Good. Let's go back. I still have some more wacky questions, and then I'm sure other people will. If you have a question about a particular slide, yeah, so I think we covered that. So let's go to the next one. Now this sort of just shows the same thing, that drier places have different years per meter.
Well, this one is a high snow accumulation rate. Okay. So when you go to, this is as it's going through the burn until it's trapped in the bubbles. So the upper part, it's mixing like down to 1 meter here. It's mixing with the atmosphere. Then
Mhm.
as you get to about say 5 meters here, the age of your gas is 4 to 10 years. So it's an average of that, and then so on and so on. Now, when you go to the low accumulation sites, snow accumulation sites, this scale is like 0 to 200. So
Yeah.
the
Wow.
gases that are trapped in here, because it's so slow going through that trapping bubble zone, it can take 100 years. So your gases are all mixed over 100 years.
Right, right. Okay, next. This just is the difference between ice and gas age, so that makes it clear.
Exactly. It's very
That-
straightforward. And
yeah.
I just wanted to go through this because Jaworski, I don't know if you're familiar with his work. He wrote a huge rebuttal on ice cores. And this was one of the things that he said, oh, well, in the 1900, we're showing, 310 parts per million, not down here where, it's really only 280 or 290 or whatever. And it was because he was referencing the wrong age of the data.
Yeah, right. Exactly.
All, all the data, and you will never really, it's really even hard to find this data in Ice Age. All the gases are usually corrected to a gas age.
And that's the right thing that's the way to normalize it.
Exactly.
Next slide. Here we go. So there's a big difference between the Eastern Plateau, which we can see is to the right of the mountains. these are completely, there's almost two continents here.
Yeah.
Okay, because everything on the right is several kilometers above sea level,
Except when you get to the edges. So
except when you get
Ball
to,
Dome is one of your highest snow accumulation rates, and DML is not, I mean, it's in between, but anything along the coast here, you get
yeah.
a lot of moisture and precipitation.
So how long are these cores? Which is the Vostok is the 800,000 year core, is that right?
Yeah, it's shown right here.
How long is that? How many meters?
Oh, 3,500 meters.
Yeah, so that's a deep core. So go back to
Yeah.
the map. Go back to the map. Yeah, here. So Vostok is 3 kilometers long, right?
Yeah.
That's a deep core.
Right, right. And so they would try to drill it even deeper, but the ice, as the closer you get to the bedrock, the warmer it gets,
Uh,
and the ice starts getting melting and distorted, and it's very ductile. It flows basically.
so is that as good as they can get from that site?
Yeah, I think I read somewhere they were trying to do another dome. Was it dome? But they were trying to do another one
Mhm.
deeper to see if they could even get, another interglacial
Yeah.
period.
Yeah. And Dome C, how long are these? Would
Dome C is one of your longest. It's around 3,500 meters too.
I see? Okay. And these other ones that Sipple, how long are how
They're about a thousand meters, 500 to 1,000 meters. Dome
on the
C is
west?
your shortest one.
So near the lower valley elevations, we're talking about a kilometer or so, or less,
Right. And
or
so
less.
these are lower elevation and they, do have higher snow accumulation.
Yeah, and you can't compare the age with the length. That's why I wanted to understand a bit about how long they are.
Yeah, it's pressure, temperature.
Yeah,
There's a lot of variables associated with it.
yeah. Right. Okay, let's go. So, and which are of these do you think are sort of best from a data quality standpoint, and which are more, contaminated or unreliable?
So, the Law Dome are your highest resolution ones, and they're very good data.
Uh-huh.
And then Dome C is the one that Brighter uses. WIS is the next one, the intermediate. And then Dome C is the one for the longer term. Vostok is, low resolution and it has pretty wide sample spacing. So that's the order. The Law Dome for high resolution, WAIS is kind of intermediate here, and then Dome C are the ones I go to all the time.
So Law Dome and Sipple are kind of in maybe in waste, or you're kind of definitive.
Sipple was an earlier course, Sipple Dome, and it it's not used that much for whatever reason, but this WAIS, the WDC right
Mhm.
here, Western Antarctic Ice Sheet is what WAIS
Mhm.
stands for. That one's a very good core too, and that one I believe covers the entire Holocene interglacial, and then it goes pretty far into the previous glacial period. That's a really good one. They've done a lot
About
of
50,
work on that.
about 50,000 years or something.
Yes,
What,
56.
do these cores get destroyed when they're measured, or
Yes,
do they
when they measure for
resample?
CO2, it's gone. The sample is gone. And that's one of the reasons because you have to have large samples, 30 to 50 grams, that the CO2 data is not as, you don't have as much of it as you do with the temperature, the oxygen isotope data. That's why you have much better sample increments with the temperature data as opposed to the CO2.
Mhm. Okay. Okay, great. All right, let's keep going. I also wanted to ask about Zwali because you keep pointing me to his papers. Isn't his name Zwali?
Uh, I'm not
Am
sure.
I
Was
confused?
it on my reference list?
No, but we've gone back and forth
Oh,
email about those papers, and I think you've told me that you thought his research was generally better than a lot of other people's.
yeah, I can't recall that one. There's thousands of them out there. Do you know what it was what part of
He's
the,
written several papers, and I've Fritz Wally, I forget his name. And
yeah,
I tend to read those because for some reason, I've come to believe that his stuff is less manipulated than others.
right.
What can you tell us about skullduggery and data manipulation in ice core data?
Uh, what kind of data manipulation?
Well, we see it in temperature data all the time, and there's NOAA has certain people wandering around the hallways doing various data tricks. And so what do we know about ice core data trickery?
Um, y- you know,
It
this
might be more on the temperature side, but I'm not
I
sure.
yeah, I would think it's more on the temperature side. I mean, the one thing that Ice core has a really bad reputation for is the smoothing or averaging of it. People don't understand the Fern process and they don't like it. And then when you start comparing it to, say, CO2 proxies from plant stomata or things like that. Plant stomata shows higher variability of the CO2, but it is much more less reliable. Um,
Huh.
they just don't want to, they want to see that there is a natural component where CO2 can rise over 300 parts per million in the past. A lot of people don't accept that the 400 parts per million, the 420
Huh.
are the,
It's
the
not
rise.
natural. Mhm.
Exact. They want it to be natural. They don't want it to
Right,
be
right, right.
all blamed on
Human,
fossil fuel emissions.
right. And the stomata, though, they just go way back much farther, many millions of years farther than the.
And they cover some of the Holocene. I showed it a plot at the CO2 Coalition meeting. They're just discontinuous, and there's a
Mm.
lot of issues with it. It's you're can't counting pores on the plant leaves, which has an inverse relationship to CO2, and then you have to have some kind of correlation with present day CO2. A lot of those correlations are, zero point 0.5 R squared or, you know,
Right.
then there's the northern hemisphere influence where you get a lot of seasonal CO2 fluctuations and just about every place in the northern hemisphere, I'm coming to the conclusion that all the CO2 sampling and anything, whether it's from uh, present day instrumental temperatures or even plant stomata, that it's influenced by these seasonal changes, by the woods, the trees, the breathing of
Yeah.
the northern hemisphere vegetation,
Yeah.
photosynthesis.
But you don't really study that much stuff before a million years ago. That's kind of not your main.
No,
That's
I
just
mean,
not covered by ice. There.
right. I mean, I have, as a geologist, I've looked at some of the CO2 data, over the past 60 million years. And I actually have a picture of it. If you, I mean, the data. I mean, what they show in the publications are these beautiful smooth curves, right? But let me show you what the data looks like. And Javier's been
Yeah, Javier went over this in
he's
his
been picking up on it.
cell. Yeah, yeah, right.
And it's ugly. I mean, it's geologic data, it's proxy data. I
Yeah,
mean, this is what it looks like. This
yeah,
is the raw data. These are the error bars associated with that
right.
data. The error bars are higher than the 100 parts per million we're seeing. And I mean, look, it's so when you see what you see in the literature, what the alarmists show you are these beautiful curves. Well,
Yeah,
who knows?
yeah, and that's what Javier. And we're gonna have Chris Cotees come talk to us in February, I think.
Okay, and Javier's already talked with you guys.
No, he's busy at the moment. I think we'll probably get, but we just watch everything he does everywhere else anyway.
Oh, right,
I'm
right.
in touch with him all the time, so I'm always ferrying information over.
Yeah, yeah.
Okay, let's go back to that slide you had before because I had a question about it.
The sample,
Yes, 12 or maybe 11. 11. Yeah, I wanted to ask here, what's up with all this stuff in the Holocene? Uh, why is there more data in the Holocene? This is just ice. You're
because when the ice, as it's buried, right, it continues to compact. So the individual layers get thinner and thinner and thinner and thinner the deeper you go. So that means so if you
oh,
systematically
temporal resolution.
no, it's not the fern, it's just the entire ice sheet. So I say I go and sample the ice core every meter, right? So when I'm in the Holocene and I sample it for a meter, those annual layers could be a meter thick. All
Uh-huh.
right. So I'm getting a sample every year.
Uh,
Now, by the time I'm down at 3,000 meters depth, those annual layers may be a millimeter thick.
yeah,
They're
yeah.
compacted. So now when I sample every meter, I've got 1,000 years in there.
Does it at some point just go linear because there's so much weight on top that the depth corresponding to the years is the same, or does it just is it just a gradient all the way down?
It's not only a function of snow accumulation and burial, but it's a function of temperature.
Uh-huh.
Right. So you got two opposing things. So it's nonlinear. The shallow part is kind of isothermal, and pressure compaction is the overwhelming force. But as you go deeper, you're getting closer to the bedrock, you're getting warmer. So now temperature starts playing a role, a bigger role.
Uh-huh. Okay. All right. If anybody has a question about any of these particular slides, just unmute and ask. I just want to go through some of these, and I've got a few more. If just pop your hand up or unmute, okay? Okay, next slide. Yeah, now here, I don't know what does MIS stand for. It's a Milankovitch term, isn't it?
Oh, it's a marine isotope stage. So the interglacials were originally named by the marine forams.
Oh,
Um, so that and so they're the I those are the interglacial terms. It's a marine isotope stage.
what do they mean? There's MIS one, two, three, four, five is I know five is kind of well known. It's the last interglacial, but but
Right.
what is it? What is MIS two, three, six, seven?
These little things in here, so they're in the glacial, what I would call the glacial period. So this MIS1, so like this might be two,
Oh,
three, five. I think this one's seven.
ah,
Mm, Yeah, like this might be 8, 9, maybe 10, 11. So, I
So
mean,
these are sediment peaks of sediment of something in the sediment.
they did temperature. The original interglacials were defined by temperature, the marine isotopes.
So it's an isotope peak. Okay.
Yeah, what they do in Antarctic, they renamed these. They don't really call them the interglacials by these names, but they call this what do they call it, the deglaciation, termination 1, termination 2,
Mhm.
termination 3, termination 4. They call these termination points. So it's the termination of the glacial. That's
It's
what they call
interesting
these.
that these lines down on the bottom, which are years,
Ice
are
ice
not,
core coverage in years.
they're not at all related to the length of the core. The length of the core would be completely different if you saw that.
Well, they are sort of. This Dome C is 3,500 feet, I believe, meters.
Yeah.
I believe Vostok is pretty similar.
Yeah.
But yeah, and it depends. They try to do these cores vertically, but sometimes if there's they do some ground penetrating radar, so they can kind of get a seismic image of them. So they avoid ice flow areas or things like that. So some of them may not be completely vertical. So
Mhm.
they may have a longer depth to them.
Right. Okay.
But
No,
generally, these are shorter cores. These are longer in general. It's not a one-to-one relationship.
right, right. Okay, good. Uh, now I also want to ask about Greenland. Let's keep going here. I think I had another question or two in the Antarctic. Yeah, this is really good. This is your data visualization, right?
Yes.
Really nice. Really helpful. Oh, yes. So here, this question comes up. We've all looked a bit at Henry's law, and essentially what we're seeing is the atmosphere is adding more. There's the partial pressure is going up because it's coming out of or going into the ocean. What can you tell us about the time lag on that?
Ooh.
Because if the time lag is 800 years, then it can't possibly affect this resolution here.
Right. So the so you're talking time lag of temperature to CO2, what they've
Right.
seen
If you go back to
historically.
the
Yeah,
800,000 years, you'd see a time lag with temperature.
right.
My
So
understanding is that mostly about 800 years, but I don't.
yeah. Okay. So basically, what they're saying is that temperature rises during these deglaciation events about 800 years before the CO2 starts coming, is expelled from the ocean. But now you got to remember that is Antarctic ice core, Antarctic temperatures. That's not global.
Sure.
So, and if you look at Antarctic temperature, present day temperatures, they don't look anything like the global temperature or the northern hemisphere temperatures. They're very different. Um,
Right.
so what some of this, so I've heard of several arguments. I think all the scientists agree that deglaciation, the orbital Milankovitch cycles initiate deglaciation, temperatures increase, and then it's a combination of decreased albedo from the glaciers shrinking, the release of CO2 from the oceans. Um, until you get into the warmer interglacial. Then and where global temperatures fit in with that, I'm not really sure.
Well, my question here is right here. We're looking, as you say, it's Antarctic temperatures here. We're not looking at the Mediterranean, are driving CO2 concentration down during the Little Ice Age, right? But how could we imagine the lag here with temperatures? Because this kind of this your LI, it looks, if I had to say what the lag is here, I'd say it's about 300 years,
Yeah.
the LIA.
They're saying, right, if the people that have actually really studied this, they're saying that the increase in CO2 here preceded the increase in global temperatures. That's what they're saying now.
For which? Post 1800?
Yeah,
Well, this is a very gray area.
it is.
So I'm less interested in that. I'm more interested in the medieval warm period and the LIA because we're only looking at CO2 here, and that's a response from ocean temperatures after some period,
Initially,
after some lag.
initially it's a response from ocean temperatures, but as you're seeing now, and as the CO2 coalition pushes quite a bit, it's also impacting
No, before
terrestrial
1800,
vegetation.
before 1800. What we're looking at here, everything to the left of 1800,
Yeah.
is
So I have some temperature plots, but I mean, from what I've seen during the interglacial period, the Holocene interglacial period, CO2 doesn't conform to global temperatures at all.
that's right. That's right. How
It's
do you?
completely, yeah, now CO2 conforms to Antarctic temperatures. I plotted that up too. I have a plot of global temperatures and Antarctic CO2, and it's pretty interesting.
Mhm.
So this is global temperatures from all the proxy data from Kaufman, which
Yeah.
is very good article. And then this is my data where I plotted all the CO2 data.
Mhm.
And here's the interglacial period. I mean, the deglaciation going into the interglacial, and where you see the low here of around 8,000
Yeah.
years, it's completely opposite of the high of the global temperatures. Now, when you plot this with Antarctic temperatures pretty much follow this trend more or less a lot better. It's more the northern hemisphere and the global temperatures that really diverge from Antarctic CO2 or what they call global CO2.
Well, that makes sense. That makes a lot of sense. And it's interesting too, because you can't really say that well, to say something about global CO2 during this period, you need a lot more than just ice cores.
For CO2.
You want to talk about global.
Well, they supposedly CO2 is well mixed in the atmosphere,
Right.
and Antarctic is, it is global CO2 is what the scientists claim.
Yeah, that's right. So, but the temperatures in Antarctica haven't gone the
It,
same way as
it as
the.
the global, exactly. Exactly.
But going back now to where we were a second ago, so I want to just understand the Little Ice Age. Yeah,
Oh,
if you can see the Little Ice Age in the CO2, that's
yeah,
driven by something. And it's basically shows that CO2 is being sucked into the oceans,
right,
right?
right.
And that's
The
being
colder water.
because the ocean's temperature has gone down a bit, right?
Right.
But
Yep.
when did the ocean temperature go down a bit? More or less contemporaneously, 100 years earlier.
Yeah, I haven't plotted that. That would be interesting, and this kind of resolution. Um,
Because the question here then is, what is the Little Ice Age temperature effect in Antarctica? What does that?
right. I know, yeah, it pretty much parallels this, but you're right. Well,
There's
yeah,
got to be a lag.
Can I add something?
Yeah, Liz.
Yeah, I was just thinking Henry's law. I mean, you're talking about an equilibrium between the snow, the water in Antarctica and the gas in the air, that's not going to be an 800-year time lag. That's going to be quite fast, I would have thought.
Where does the time lag come from in the 800,000 year reconstruction? Maybe that's comparing with world average.
I mean, you're talking
Temperature.
then about the turning over of the oceans and the whole system coming into equilibrium with the atmospheric carbon dioxide. That's a different thing to talking about a very localized equilibrium between the gas and the snow, the liquid, or the gaps. That's what it seems like to me. You're not in Antarctica, you're looking at a very isolated system. You're not looking at the whole thing averaged over a huge area and huge depths and whatever else.
Maybe that's it.
I don't know, but that's
Yeah.
just a thought.
Yeah. Okay. Okay, let's keep going. That's good. I think that makes a lot of sense that we're comparing to local temperatures there. Next one. I don't know if I had yeah, I think this is much of it. Anybody else have any questions on these next slides? The temporal resolution is a big deal, which you can see right here. And you can't make the mistake of using the wrong. And you've written about this in What's Up With That. There's just not, the data only tells a certain story and it doesn't tell the story, as uniformly as you'd like.
Right.
I'd like to switch to Greenland now.
Okay.
You studied the Greenland. There are how many ice cores in
There's
Greenland?
like 10
7?
ice cores in Greenland.
Yeah, right. So tell us about that data and what do you think of it?
Well, I originally so you already mentioned all the caveats with Greenland, right? In the beginning, the melt layers,
Contamination.
yeah, the melt layers, the impurities, the seasonal influence. And scientists, they won't even show Greenland data anymore. But I do have a plot.
But you defended it, I
I
believe.
did, and Ferdinand kept, giving me a hard time. And and I am coming, I mean, so here's what Greenland data looks like. I did put in, if I can find, can you guys see that?
Sure.
Anyway, so here's what so this red line is the Antarctic data. And the Greenland data is shown in green. And so I ended up getting rid of all the wet extraction data, right? Because it was really erratic. So this is just all dry extraction. So there's a little bit of, this was a very detailed study on Greenland by Barnola, and it actually makes a lot of sense. It's pretty much in line. And then here you can see, then you don't have any Greenland data till you get to the end of this deglaciation. And you can see that you get a lot of variability, high and low. And
Why
then
is it so clumpy?
why is it so what?
Clumpy.
Why is it so funky?
Clumpy. Why is there so much space between and then there are a lot of data in a short space?
Because when they started seeing the really erratic CO2 measurements from Greenland, they did some test intervals, but they simply quit sampling the Greenland cores for it. So there's just not a lot of samples. I mean, this study, they went in, I think they were trying to image the key events, like the deglaciation here, one of these little, in the glacial period, one of these little DO events, I think they were
Uh-huh.
trying to hit.
Well, that's not the DO events are every so many hundred years, not on this scale.
Yeah, the CO2, now remember, Antarctic data in the glacial periods are going to be even more smooth, right? Because you don't get a lot of snow during the glacial periods, right? It's dry. So you do have quite a bit of smoothing in here. So I don't think this excursion's right, but I think this one's has seasonal implications in it. It could have some acid carbonate reactions. I think that's what distorts some of it. That's what the scientists say anyway. The one thing though that surprised me is that it rarely gets over 300 parts per million either. I mean,
Mhm.
it's really here, and you get a little bit over here, about 325 parts per million in Greenland, which is
Mhm.
another reinforcement that we really didn't get over 300 parts per million 20, 30, 40, 50,000 years ago. It's just another reinforcement because you'd think Greenland would see it.
So
It
are you coming around to Greenland isn't really very useful data in total?
I think I never throw out data. I think every piece data point is trying to tell us something.
Yeah.
Um, I think on this shoulder event here, I mean, you have a major change here when you're going through these deglaciations to all of a sudden you're stable, whatever's stabilizing this, I don't know. The stomata data goes crazy right here too. You get really high variability.
Well,
So
this is the younger Dryas, so of course.
right, exactly.
Sure.
And I think maybe you get a lot of contamination from the vegetation. The plants they just greened up right here, and you could have you know huge CO2 seasonal fluxes from the plant
Mhm.
that maybe Greenland's capturing some of that.
Mhm. Mhm.
You've seen let me
Plus, they were raising cows and goats back then, and that's
yeah,
all. Think about all that flatulence. I mean,
right, all the farting going on.
right. I mean, geez.
Let me show you. This plaque this drives me crazy too. So what, right? This is modern instrumental data, and this is from 2020 to 2005. And this is CO2 over here. So this
Northern Hemisphere. Yeah.
look at the northern hemisphere. The, this one, so the green is Mauna Loa, and the South Pole is this black line. So they all show this same underlying trend. So this is the well-mixed underlying long-term trend. But look at these seasonal fluctuations. This brown is from Maine, okay?
Huh.
They
Huh.
have a tower in Maine where it's goes up to 108 meters. So
Huh.
these fluctuations here were taken at elevation plays a role. So they get these inversions in Maine, right?
Yeah. Uh-huh.
And so just think you got all this floating around in the northern hemisphere, and I just think some of the the vegetation, the terrestrial, the plant stomata, and the northern hemisphere Greenland ice cores are capturing some of that data. So you get some data here, you get some data here. I mean, so you get all this flexibility. I mean variability. It's
Much noisier.
in the northern hemisphere. And
Yeah,
that's where all the plant stomata data is from too. That's where all your birch and your
yeah, noise.
judicial trees. Yeah. And so
Yeah,
that's where I'm headed, Dave. I'm not sure there are that many acid carbonate reactions, but I think it's the northern hemisphere, especially when you get a big greening, um, you get very wild CO2 seasonal swings.
right, right. And just for people's interest here, if you could possibly visualize this with north and southern hemisphere data at the same time, you'd see a phase shift of 180 degrees. So every six, so it'd be
Oh,
6 months
I have
shifting.
that here.
You have a visualization? It's tricky.
Oh, this is Barrow. So this is just over a 2-year period. And then this is so you can see when the plants photosynthesize, they consume CO2 during the summer.
That would be summer.
That's summer, June, July, and August.
Right.
And then um, during the winter, they go into a dormant period. And so they're not sucking in all that CO2. It's released. And so you're fluctuating here annually, I mean, seasonally by 20, 25 parts per million. This is South Pole. This is all instrumental data. This is the South Pole station, and you can see it's 1 to 2 parts per million. Now, they all show the same underlying trend. Oh, and these are some global pictures. I think they're models, but during the dormant period, your CO2 is very high in the northern hemisphere
Yeah.
by over 20 parts per million of what it is in the lower. And I just think, so every time I look at some northern hemisphere data, you see these nice fluctuations in the plant stomata and everything. And I think this is my personal opinion. I haven't read this anywhere, but it's capturing some of these seasonal fluctuations. And so I don't know whether I'm plotting a data point here or a data point here. You know, that's kind of where I'm headed.
If you could see Tasmania, you'd see the inverse of this.
Oh yeah, yeah. So I don't know. But at least in the South, they all show the same underlying trend right here. They're all gradually increasing.
Sure. Yeah. Well, this is 2005, of course.
Right.
Do you know about the NEEM project?
The neem or me?
NEEM ice core in Greenland.
I know a little bit about neem. Is there a new project?
Well, there's a whole movie about it
Ah,
where this is the interesting thing. I don't know if you know, but they drilled, I don't know how far, 1,500 meters, I'm not sure. And then they dropped a very sensitive apparatus down the hole, and they actually measured the temperature of the ice in the hole going down.
oh,
Are
yeah,
you familiar with this?
they've done that on a couple of the Greenland ice cores, borehole temperatures.
Or hole temperatures.
Yes,
Right.
yeah.
Is that legitimate or is that nonsense?
No, it's legitimate. It's very low resolution though.
Mm.
Oh, for temperatures.
I mean,
The
because you gotta imagine, I can imagine a whole bunch of ways that could just produce noise.
Yeah, there's probably some background noise. And then
You've
when
got the hole is breathing.
well, the other thing too is at the surface, there's an temperature and it's heated up,
Yeah.
when you have all that equipment sitting on it and
Yeah.
cooling. So
Right.
there's like a little inversion up there. So they have to correct for that. Um, they use those temperature profiles in the global temperature data, but it's pretty low resolution. But it does show the Holocene
Uh-huh.
climate optimum, and it shows the little ice age. So it gives you a general trend. But the ice cores have much higher resolution.
I'd like to interview the guy because it's an interesting movie and there's kind of a lot there to unpack. So
I think I have seen that.
but you don't have contact information for him, do you?
Mm-mm.
Team. Okay. All right. Anybody else want to ask? I have monopolized as usual, so I'll just, okay, why don't you stop? You want, well, they might want you to show your slides. Let's go to Tony.
I was just going to ask about the process of diffusion. Are you referring to the trapped air moving out of the ice, or just spreading out in sort of 3 dimensions and contaminating adjacent areas of partially trapped gas? And also, do different constituents of the atmosphere behave differently? Sort of certain gaseous components diffuse quicker and maybe cause a difference in the concentration of the trapped gas over time, and that also might include any chemical changes with the surrounding water. How complicated is it, and how is it defined?
It's definitely complicated. And my understanding is that you only get diffusion out of the ice in the first top meters where it's more of a convection mixing. It's not really a diffusion, but it's like a wind. Wind can mix the gases in and out of the ice. But as you get below 2 or 3 meters, I think most of the gas diffusion, and the law that I've seen quoted is Fick's law of diffusion, where you have the gas gradient and the density of the ice fairly well. It's pretty easily, and then the pore volume, and that's how they build their models. So I think most of that diffusion is pretty much contained, as you saw by that one model, within several meters, and it changes as you get deeper and deeper and deeper. There are, as far as chemical reactions, the one I think that is most concerning is if you have water, and that's the solubility of CO2. I don't think any of the other gases are altered that much. Nitrogen. So basically, the gas component trapped in the ice has these similar components of the atmosphere. So it's like 78% nitrogen, 21% oxygen, less than 1.9%, less than 1% argon, and then your other minor constituents, which are CO2 and methane, and a couple others. So supposedly those concentrations that are trapped in the air bubbles are very similar, with the exception of some of the thermal gravitational effects of CO2. The heavier CO2 happens to be a heavier molecule, so you do increase, the CO2 is increased a little bit by the time you're trapping these gases in the ice. But nitrogen is pretty benign, and they'll do a lot of their baseline projects, or when they're evaluating the gases, they do a lot of evaluation of the nitrogen kind of as the baseline to make sure they're not getting a lot of compositional changes in the gases. They'll also measure the total gas as you're going through the ice to make sure there isn't loss of the total gas. So when they partition it out or measure it. you have pretty much the similar composition of the air. So hopefully that addressed some of your questions. I'm not a chemist, so
Neither am I.
Liz,
That actually answers some of my questions. So they don't just measure the carbon dioxide, they measure the
all
whole.
of them. Yeah.
all.
Yeah,
So,
I just focused on CO2, but when they go in
Yeah.
and do a gas evaluation, they measure all the gases, the nitrogen, the oxygen, argon, methane, CO2.
right.
Yeah.
So, yeah, I was going to ask you, said about the wet method and the dry method. So is all that data that you showed for the Antarctic ice cores measured with the dry method, with the sublimation method?
No, most probably greater than 50% of them use the mechanical dry method. So, and there isn't a really big difference, maybe 1 or 2 parts per million, but no, they all use the dry method, but not all of them use the sublimation method.
Okay. It's pretty impressive data.
It is a very
It's really
impressive data set.
data.
Mm-hmm.
Yeah, yeah.
It
And
is.
it really gives a good, baseline for everything else for the past 800,000 years, doesn't it?
Yeah, it is definitely the gold standard, and it's the
Yeah.
one that everybody refers to, and
Yeah.
it's a great
Yeah.
database for natural variability.
Yeah. And as you say, the Greenland data, you're not going to know which season it's measured in because the resolution, the time resolution is just not up to it.
Right. Right. I
yeah.
wish they would publish more of the data, but yeah, I don't know how you have to develop some kind of model to get rid of the seasonal variability and the meltwater layer influences and yeah, I don't have access to those really sophisticated models. So mine's more Excel spreadsheets.
Anyway, fascinating. Thank you so much.
Yeah.
you go back to the MIS slide that shows the 800,000 years. Who else has a question?
Oh, here's a more blown up one. This has
Yeah,
temperature and CO2 on it.
this will show the lag better.
Well, so remember I told you the gas age, ice age shift. So first of all, the ice age probably has a 100 or 200 year error bar on it. And then the gas age, they shift it around. So I have no problem shifting these curves. But anyway, these are unshifted data. This is what they present. So here you can see, can you guys see that cursor?
Yeah.
Okay, here you can see if you zoom in on these, and I have zoomed in on each one of these interglacial periods, but you can see temperature is going up. Temperature's in black, CO2's in red. And temperature is going up before CO2. You see that in a couple places. You see it over here in the last interglacial. The one thing that also is the length of CO2. This MIS 11 one, you can see CO2 even, it's pretty close to the deglaciations, but when you start building your glaciers again, here temperature dropped by very, very soon before CO2 just hung out there for a while. You can see that on the last interglacial too. Temperature dropped and then CO2 is still
But what you're saying though, Renee, what I see on the legend is that this is the dome C temperature.
it is.
So you'd expect less of a lag there than possibly if you look at the global temperature, as we said before.
Right. Somebody, God, I can't remember his name. There is a study on the Holocene interglacial deglaciation, that plotted not only the Antarctic data, but the global proxy data. And they found that the CO2 preceded the global and northern hemisphere. So what they were inferring, I believe, is CO2 went up. It enhances or modifies the global and northern hemisphere temperatures. So
That sounds like NASA to me.
yeah, yeah, yeah. The problem is we don't have I mean, this is Andy May's big beef. What is the global temperature? We don't know.
Sure.
I mean, the northern hemisphere temperature is completely different, even in Greenland ice cores, than the southern hemisphere temperatures. And we don't really, the tropics doesn't hardly change at all. So, it's latitude dependent, and uh, how meaningful is a average global temperature?
Right, for sure. So, but what you said was interesting to me that I had never thought of, which is that during the interglacials, there's a lot more precipitation. So on a scale of hundreds of thousands of years, you have these dense periods, and then you have these less dense periods, and dense and then less dense, going down the core.
Yeah.
Right. And it would
Yep.
be interesting if you could visualize that. Maybe that'd be an interesting slide. You know, if you could show that density going along time.
Yeah.
To get an appreciation of that.
The other thing that's really interesting is if you ever look at their temperature curve with depth, that is very crazy. I mean, the Holocene is really expanded, like depth is so nonlinear because of the densification and the compaction. You can barely even see these. And I mean, they're very suppressed. It's it's very interesting.
Yeah.
I don't have that with me, but
It would seem to me, because as everybody can see here, and I've pointed out in previous talks, that temperature tends to go up quickly and down slowly.
yeah.
And that's sawtooth pattern of the Milankovitch cycles. And what you'd see in the density is that as temperatures go up quickly, you're going to get densification early in the core. And then as temperatures work their way down, you're going to find that density relaxes slowly going down the core. You'll see some similar effect in the density as you go down the core.
Right. So these are going to be, low snow accumulation, very dense, and these are going to be less dense. Yeah.
Isn't there more density when it's warmer?
Well, with the melt layers,
There's more precipitation.
yeah. Higher
Right?
accumulation.
Yeah, and when it's really cold, it goes it accumulates much slower.
Right, right. So
Right.
it takes it a very long time to get buried.
So your core would be densest during the warmer times, no?
Yeah, I don't know.
That's when you've got more compaction happening with more
higher
weight.
precipitation.
Over 100 years, you get a lot more weight of snow coming down.
Right, exactly.
Right. So
It moves faster through the whole densification process.
Yeah. So that density would be really interesting to visualize. Maybe somebody has, I don't know, but I hadn't thought of it until you mentioned it. Tony, you got to unmute.
Thank you. Is the temperature on this graph the borehole temperature with depth?
No, this is from ice cores.
This
So-
is isotope, right?
Yeah, oxygen isotopes.
Right. Okay.
Anybody have any other overall questions or?
So, sorry, can I just clarify? So that does show an 800-year time lag, or
It does. It's hard to see
More
because
than others.
I'm not, yeah, it depends which interglacial period you're talking about, or deglaciation. They don't all have exactly a 800. There's one or two that have a 800, others have less.
You can see there's more of a lag on the downslope than on the up.
Exactly.
So it's nonlinear. But what your overall message, Renee, is that the work on most of these cores in Antarctica is pretty good.
It is.
There
I-
isn't that much trickery, and the resolution is, people are pretty good at saying what's there and what isn't.
Right.
There isn't a lot of jumping to conclusions and imagining and infilling and normalization, what do you call it, averaging,
Yeah, the smoothing, yeah.
smoothing and all that other stuff.
There is towards the end here, right? But the high resolution cores up here, you know, you do have very good data up there.
I think for the last 2,000 years, it doesn't make sense to talk that much about ice core data, really. It's just, it's too noisy. Don't you think?
For the last 2000?
Yeah.
Oh, it overlaps pretty good. It's not too bad.
So
Oh,
maybe,
you mean the last the eight,
maybe this last 300 or 400 are less reliable,
the deeper and the older, right?
better. Yeah. Right.
Yeah, but in general, I mean, I concur with your initial comments that the ice core data, I don't think they're hiding anything or there's any trickery. I think it's reliable, a good data set for the CO2. Um, and it's not too bad for the temperatures. The temperatures tend to be a lot more noisier because you have so much more data.
We'll invite you back to go over that if you have time in the spring.
Sure. It's
Great.
it's a entirely different measurement, which is why I didn't want to, you know, throw
Sure.
too much information out. So anyway,
All right. Anybody else? Any questions? I don't want to cut anybody off. Anybody? Our science team? Okay. All right. Thank you so much, Renee. That was just really fantastic. We really appreciate it. We love your visualizations and the way you present the data. It's really stunning, and it's been a real treat.
well, good. It's fun talking about, especially when you plot up all the data and can make some of your own observations instead of just taking other interpretations for granted. So
Yeah, great.
thank you for inviting me, Dave.